All right, onward. Our last part of this lecture, lecture 24, part C. So we're going to talk about one more idea involving gases, one more gas law. Before we do that, maybe we should do another one with stoichiometry. Those can be a little tricky, huh? So let me show you one more example with stoichiometry, and then we'll get into that final gas law I want you to be familiar with. All right, let's flip over. We'll get started. All right, let's do this example. All right, so it says if this reaction is done at a pressure of 892 torr and a temperature of 368 Kelvin using 8.85 liters of nitrogen, how many grams of, I guess, ALN, aluminum nitride would form? How many grams of this are we going to make? All right. Now, let's see, what have they given us? Well, they've given us a lot of information about nitrogen, actually. If this reaction is done at a pressure of, I'm going to go ahead and put all those numbers with the nitrogen because they have to do with the gas. So this reaction is done at a pressure of 892 torr. That's probably got to do with nitrogen. And a temperature of 368 Kelvin using 8.85 liters of nitrogen. How many grams of this stuff are we going to make? All right, so yeah, this is definitely a stoichiometry problem. They tell me a lot of stuff about nitrogen. They want me to figure out how many grams of ALN I would form. So we're going to have to, let's see, we're going to have to figure out, well, first off, if you think about all stoichiometry, it really involves moles, right? So if we could figure out how many moles of nitrogen we have, we could go to moles of ALN, that moles of one thing to moles of, yeah, we would use our coefficients there, wouldn't we? And then once you went to moles of ALN, then you could go to back to grams of that. Oh, we would use our periodic table. So kind of the new thing is, well, how are you going to get to moles of nitrogen? Well, that's why they're telling you all these numbers about this gas. We can plug all of these in. We'll put them into PV equals nRT. Once we put them in, and we'll double check we have all the numbers we need and they're all in the right unit. I think what we're going to need to do is then solve for moles, and that'll be moles of nitrogen. And then once we get moles of nitrogen, oh, that's kind of like what we were doing before. Moles of one thing to moles of something else. And then once we get to moles of that, we'll go to grams. All right, so the first thing we need to do in this example, we're actually going to have to use PV equals nRT first to solve for moles of our gas, moles of nitrogen. All right, let's go ahead and do it. All right, gosh, I probably need a little more room here. Well, we'll try to make it work. All right, so to do PV equals nRT, maybe I'll make a list this time. PV nRT. They've told me the reaction is done at a pressure of 892 torr and a temperature of 368 Kelvin using 8.85 liters of nitrogen. So what I think I need to do, I need to solve for moles of nitrogen. We have everything. Oh, R is always that same number. Yeah, so we do have everything. 0.08206. Okay, so I think we're going to be okay using PV equals nRT because we got 4 out of the 5. We can solve for the one that's missing. The one that's missing is moles. All right, now, before we start, got to double check your units. All right, so let me ask you a little question here. Do any of those numbers need to be converted? Are any of them in the wrong unit for PV equals nRT? Yeah, it's pressure. Pressure is in the wrong unit. Pressure needs to be in atmospheres. So let me go ahead and convert it. I'd use my conversion sheet, and let's see here. I think the conversion, it should look something like this. 760 torr is 1 atmosphere. So if you convert it to atmospheres, you're doing this at 1.17 atmospheres. Okay, so now we have everything, and we have it all in the right unit, because liters, yeah, that's good for volume, and Kelvin, yeah, that's good for temperature. So let's go ahead and do our math. Let's go ahead and plug in. PV equals nRT. The pressure of my nitrogen, the volume of my nitrogen. Moles is what I'm looking for. R T. All right. So we're going to solve for N. All right. So how are you going to solve for N? Oh, we're going to have to take both sides, divide. Divide by what? Divide by 0.08206. Because that's going to cancel over here. And we're also going to divide by 368. All right. Oh, it's getting a little messy. That's the temperature, 368. Oh, 368. Okay, because that's going to cancel as well. All right, so this is what you'll get left with. Gosh, can I fit it in here? All right, I'll just write it up in this corner. I think we'll be okay. All right, let me go and write it right here. N would equal this. The number of moles would be this, PV. And then on the bottom, I'm just recopying what you see over there. This is on the bottom, and so is the temperature. All right, so if you get out your handy dandy calculator, you type it in, the moles, you end up with 0.343 moles. Now let's be clear, that was the pressure of nitrogen, the volume of the nitrogen, the temperature of the nitrogen. This is going to be moles of nitrogen. Moles of nitrogen, 0.343. All right, so we are right here. We have moles of nitrogen. What we're going to do next, we're going to look at our coefficients and now start thinking about what I'm solving for. Go to moles of ALN. Now, this has really turned into a big old mess because there's a lot of work and a small screen. So if you need to writing this down, you could pause it for a sec. I'm just going to move on, and I have to erase some of this, so you can pause it if you need to. Let me go ahead and keep going. All right, we're done with this stuff. Erasing time. Try to avoid doing a bunch of erasing, but gosh, sometimes you need to. All right, let's clean this up a little bit. Let's see where we're at. All right, so we just have moles of nitrogen. So now we're going to go to moles of what I'm solving for. Moles to moles. Oh yeah, that's coefficients. I am solving for ALN. All right, now we're going to look at our coefficients. So for every 1 mole of nitrogen, I am going to get 2 moles of aluminum nitride. I'm using the coefficients. Now, if you work it out, you are going to end up making 0.686 moles. All right, let me just tell you from past experience, when people have done this, this is the step they tend to forget. So make sure you think about, oh, I need to go from one compound to another. I need to use my moles. I need to use my coefficients, I should say, to do that. All right, so at this point, we're now going to go from moles back to grams. We need to use our periodic table. So let me go ahead and take that answer, and we'll have to add up to weight off the periodic table, and that's how you get from moles to grams, right? So you got to add up 1 aluminum and 1 nitrogen. Aluminum, 26.98, I should say. 1 nitrogen, 14.01. There's only 1 of each. So if you put it together, oh, when I did it, I got 40.99. 40.99, and oh, that's going to be grams equals a mole. All right, so think about it. One last question for you on this one. What are you going to do with the 40.99? Multiply or divide? You're trying to go from moles to grams. What do y'all need me to do? Multiply or divide by 40? You should multiply. You'd put the 1 mole on the bottom. You'd put the 40.99 on top. If you work it out, when we did this reaction, you're going to end up making 28 grams of aluminum nitride, 28.1. All right, so I know these are a little tough. Tends to be one of these problems people get a little stumped on. So yeah, we'll probably do another example or two in Zoom and give you a little time to practice this so you can feel okay about it. All right, there's one more gas law I want to talk about. So let me flip over one more little topic that I want to fit in here. Let's flip over and we'll talk about it. Okay, one last gas law. All right, so and that is, it turns out gases often are mixtures. So you don't usually have just pure oxygen or pure nitrogen or whatever. So for example, air. Air is a mixture. Air is, well, it's mostly nitrogen, the stuff you're breathing right now into. There is oxygen in it. Thank goodness. We need that to stay alive, don't we? And then there's a bunch of other little minor components of air. Like, for example, right now, when you take a big old deep breath, you're actually breathing also some argon. Argon is also present. And then, depending on how detailed you want to get, there are more gases. Carbon dioxide, other things too. All right, so turns out that when we have a mixture of gases and we want to think about the pressure of them, the pressure of any of these gases is called a partial pressure. It's called a partial pressure. So it turns out, and this is not always so obvious, but it turns out pressures, you can add them together. And the guy who figured this out was a guy by the name of Dalton. So Dalton, you might have remembered we talked about him before when we talked about atoms and the atomic theory. He also figured out that pressures of gases add together. All right, pressures of gases add together. So a pressure of any one of those three, the nitrogen and the oxygen and the argon, that would be called a partial pressure. If I want to know the total pressure, you can just add them. So right now, for example, the pressure from the nitrogen in the air, I guess we'd call that the partial pressure of nitrogen. It is about 593 torr. The pressure from the oxygen in the air is about 160 torr. And the pressure from argon in the air, it's about 7 torr. So all of these would be partial pressures. They're the pressure of one of them. Now, if I want to know what's the total pressure of all the air, you can just add them up. So if you add them up, the pressure together, it adds up to 760. It might sound familiar. That's kind of normal pressure, right? All right, so this idea that pressures add together, that's called Dalton's law. I guess I should have written this way, Dalton's law. Dalton's law. Yeah, Dalton's law, the pressures of gases add together. All right, so let's do just one quick example of this. Let me flip over to the last slide here. And let's see here, it says a mixture of gases contains nitrogen, hydrogen, and oxygen, and the total pressure is 695 millimeters of mercury. If the partial pressure of nitrogen is 435 millimeters of mercury, and hydrogen, it's 205 millimeters of mercury, what's the partial pressure? How much of the pressure, in other words, is coming from oxygen? All right, so let me kind of talk about this maybe a little bit more in detail than what the first example I did. So whenever you have a mixture of a gas, the total pressure, I'm going to write P total, will equal the pressure of these gases added together. Now in this case, there's 3 of them. Maybe this is like a tank and it's got 3 gases in it. Nitrogen, hydrogen, and oxygen. So all of those would be called partial pressures. And the thing that Dalton figured out is that the total will add up. Those 3 will add up to the total. So if we look at this question, it says a mixture of nitrogen, hydrogen, and oxygen has a total pressure of 695 millimeters of mercury. If the partial pressure of nitrogen is, okay, they're telling me the pressure of nitrogen, and the partial pressure of hydrogen is, all right, they're telling me the pressure of hydrogen. Well, they want me to figure out the pressure from oxygen. All right, so we can figure that out. And we're going to have to do a little algebra. And this time, notice that there's plus signs there, right? So we got to move things from the right-hand side over to the left-hand side. Now, since there's a plus sign, the way you get them to move, you don't divide by them. I'm not going to divide by 435. The way I'm going to get 435 to go over to the other side, you do the opposite. Since there's a plus sign, you're going to subtract 435. You do it on the right, you got to do it on the left. And we also need to move over the pressure of hydrogen. There's a plus sign there, so we're going to also need to subtract 205. Do it on the right, you got to do it on the left. So these numbers are going to cancel, and we'll be left with this. The pressure of oxygen equals this, 695 minus 435, oh, I have enough room there, minus 205. If you work it out, you know what, I actually haven't done it yet. Let's do it. Let me get out my calculator. Oh, I gotta go over and reach for it. All right, 695 minus 435 minus 205. Oh, you should get 55. That's what I got, 55. Oh, and they would be millimeters of mercury. All right, so that's the last example. We're going to do some other examples, a couple other topics I didn't get to in these videos on Zoom. Some people like this stuff. If you like math, yeah, it's been all math basically, right? If you don't like math, maybe this hasn't been your favorite week. All right, sorry about that. In any case, hopefully it's making sense, and that's it for gases. So in our next lectures, we're going to move on to something different. If you have any questions, like usual, let me know. I'll be glad to help you out. Bye-bye for now.